Hello, everyone. Good afternoon. Anyway, um, I'm really glad that you guys are here and that you are listening to me. I was just saying that it's amazing that we as humans have been able to sort of figure this chemistry thing out, right? Because there's these particles that are just so small, you can barely even imagine them. Remember, a single grain of sand from East Beach has more atoms in it than all of the sand grains on the beach, right? That's how small these particles are. And yet the properties of everything we see around us depends on the structure of those particles, right? And that's the big story of chemistry, and that's what makes chemistry exciting. And that's what I love about being a chemist, is being able to see the world around me sort of in this new way. So anyway, we do have the semester is already going by, crazy enough. We have our first exam just right around the corner. It's next week on Thursday. So make sure you have that on your calendar. It's Thursday, February 11th. It'll cover chapters 12, 14, and 15, right? And you'll have a big window, probably from 11 a.m. to midnight or so, to take the test. The test itself will be 70. You have a time-limited test of 70 minutes, okay? Unless you have DSPS accommodations, in which case it'll be adjusted accordingly, all right? So we finished chapter 14 already, right? Which is this chapter. So we just have chapter 15 left to cover before the exam. Chapter 15 is on reaction rates. I hope you all saw the videos before coming to class. Those videos hopefully help to break in some of the ideas that we're going to be talking about today, okay, and get you introduced to them. Do you have any questions for me before we get started? Megan.
I know this might sound kind of silly, but I'm still confused on when it's going to be like negative rate of change or when it's going to be positive rate of change.
Right. Okay. So I'm going to do some examples today that hopefully will clear that up a little bit. But if you're defining the reaction rate with regard to a reactant, since reactants go down in concentration, you put a negative sign in there when you're defining the rate of the reaction. If it's with regard to a product, products go up in concentration, so they're naturally positive. The point is, we always want the rate of reaction as defined to be positive. So if the change in the concentration of some is negative, like in the case of a reactant, then we put a negative sign in front of it to make it positive, right? And I'll cover that in more detail in just a minute. Are there any more questions before I start? Sophia. Sophia, are you there?
Yes. Sorry, my hand option is kind of weird.
No problem.
On Megan's question for the post lab due today, there was number 7, I think it was. That should be a positive or a negative, because it was the change in temperature, the delta TF after adding the solute to the solution.
The post lab today was on reaction rates, right?
Mm-hmm.
Sorry, the pre lab, oh, sorry. Are you talking about the lab or the lecture?
The lab.
Oh, shoot. You know what? I don't have that on the off the top of my head. I'd have to go back and look at that. Maybe just hang out after class and ask your question, and we can jump into that a little more then. Is that okay?
Yeah.
Okay.
It's just about like reaction rates. When it's reaction rate, should it be negative or positive? Like if it changed from 0 to negative 2.1, should the change?
I see. Yeah. Then yeah. So it depends on what you're defining. So let me. So this is. I'm going to jump into this right here at the beginning of class. So hang tight, and we'll talk about that. Okay. Let's go ahead and get started. So the first thing we got to do if we're going to talk about reaction rates is define rates. Oops, that's way in the wrong place. Is we got to define the reaction rate, and I'm gonna skip through all this because we already covered this basically. And I just want to go to this example. And I want to give you the overall definition of the reaction rate. So the reaction rate, the definition of a reaction rate, if you have a reaction A plus B goes to C plus D, where the capital letters are the reactants and products, and the small letters are the stoichiometric coefficients, okay? Then we define the rate like this. We define the rate of this reaction as being equal to minus 1 over A delta time. Or that's if we define the reaction rate with regard to reactant A, right? If we define it with respect to reactant B, then we would write minus 1 over B delta T, okay? These negatives are here. Why? Because delta A delta T is negative, right? If you think about, if we go back to these kinds of plots, right, where you look at a reactant, reactants go down in time, right? So if I have this reaction, the concentration of H2, which is this one, goes down in time, right? So notice that slope is negative. The change in H is negative. So because this quantity is negative, we put a negative sign in front. And what does that do? It makes the overall rate as defined a positive quantity. Okay, so whenever we talk about the rate of a reaction, always positive. Whenever we talk about the rate of change of a reactant or product, that's going to be negative or positive depending on whether it's a reactant or product, right? So if it's a reactant, the rate of change of a reactant concentration is what?
Negative?
Negative. Exactly right. If we're talking about a product, the rate of change of a product concentration is what?
Positive.
Positive. Okay. But if we're talking about a rate of reaction, that's always going to be what? Positive, right? It's always going to be positive. Why? Because if it's a reactant, we put a negative sign in front of it to make it positive. Yeah, are you with me now? Does that make sense? Okay. If we're defining with respect to products, we're going to no negative sign, but we still need the stoichiometric coefficient, 1 over C delta T is equal to 1 over D delta T, right? So you can define your reaction rate with regard to any reactant or product, right? According to this definition. Okay? So again, to repeat again one more time, the rate of a reaction is always what?
Positive.
Positive. Okay? That's different than the rate of change of concentration of a reactant or product, which is not the rate of the reaction, right? This is the rate of change of A with respect to time. This is the rate of change of B with respect to time, etc. That is not the rate of the reaction. The rate of reaction is defined only like this, and it's defined in such a way that it will always be positive. Okay? Does that make sense? The rate of change of reactants, this quantity is always going to be negative for a reactant, right? This one, always negative for a reactant. The rate of change of C of a product, always positive. All right? And the rate of reaction, always positive. Okay, let's do a little example so that this becomes crystal clear and there won't be any more confusion. All right. So here we have a reaction. The I minus changes. So we're given that the I minus concentration changes from 1.00 to 0.868, right? In 10 seconds. Delta T equals 10 seconds. Calculate the average rate of reaction in the first 10 seconds. So we want to find two things. We want to find the rate of the reaction. Okay, that's the first thing. And in addition, we want to find the rate of change of one of the reactants, delta H, delta T. Okay, and by the way, I think I said this last time, but any quantity like this in brackets means the concentration of that thing, and it's usually in molar. moles per liter. Okay. That's what these brackets mean. The concentration of that thing, whatever's in there, in moles per liter. Okay. So let's start with finding the rate first. Okay. So let's use the definition here and apply it to this reaction right here. Okay. And since it's giving us the change in I minus, let's define the rate of reaction with regard to I minus. Okay. So here's I minus, right? So first of all, when I write the definition, is I minus a reactant or a product?
Reactant.
Reactant. So is it going to have a negative sign in front of it or not?
Yeah.
It will, right? It's going to have a negative sign in front of it because it's a reactant. So rate is equal to minus, and then I notice a coefficient of 3, right? So what do I have to do? I take 1 over 3, right? So that's 1/3, right? Times the rate of change of I minus over time, right? Delta I minus delta T. Does that make sense? That's just applying that definition to this reactant, okay? So now, in order to get the reaction rate, I got to figure out, okay, well, what is delta I minus delta T? Okay, delta I minus delta T. Remember, delta anything is final minus initial, okay? So here's the change in the I minus concentration. So that's going to be, the numerator here is going to be 0.868. That's final minus initial, right? Divided by delta T, well, it told us that was 10 seconds. Okay? So that, if we work that out, that's equal to negative 0.0132 molar per second. So notice what I've just calculated. I've calculated the rate of change of a reactant in the reaction, right? Is that the rate of reaction? No, right? The rate of the reaction is minus 1/3 times that. This is the rate of change of I minus. Why is it negative? What is I minus?
Reactant.
This is a reactant.
Right? So it's negative. But now when I apply the definition of rate, I get rate is equal to minus 1/3 times this quantity, negative 0.0132 molar per second, right? And so that turns out to be equal to 4.40 times 10 to the minus 3 molar per second. Okay, and that's the rate of reaction. All right, so it's important to distinguish between the rate of reaction, which is given by this definition, and the rate of change of any individual reactant or product. Those are two different things. Are you with me? Awesome. Okay, the question asks, there's a second part of this question. Now we want to calculate delta H plus delta T. Well, we already know the rate, right, is this. So why don't we just say, okay, let's find out how the rate depends on delta H plus delta T, right? So we can apply the definition again. And if we define the rate of reaction with regard to H plus, what's that definition? Well, first of all, this is a reactant, so it's negative. It has a 2 in front of it, so I have to have the 1/2. And then it's delta H plus delta T. Okay? So I know the rate is this, right? So delta H plus delta T is equal to negative 2, right, times the rate is equal to minus 2 times 4.40 times 10 to the minus 3 molar per second. And that's equal to negative 8.80 times 10 to the minus 3 molar per second. Does that make sense?
Sorry, I couldn't hear. What are you calculating now?
Pardon me, repeat that one more time.
What are we calculating on this second step?
On the second step, we're calculating the delta H plus delta T, this quantity. In the first step, so 2 steps. The first step, we calculated the rate of reaction, that's here. The second part, we calculated the rate of change of one of the reactants. Does that make sense?
Yes, thank you.
Awesome. Good, good, good. Okay, now without doing any calculations, let's see if you can tell me this. So here you know that the rate of change of delta H plus delta T is equal to 8.8 times 10 to the minus 3. So what is, if you know that, then what is delta I3 minus delta T? Without doing any calculations. Just think about it. So two things to remember. One is that this is negative because it's a reactant, but this is a product. So is it going to be negative or positive?
It's going to be positive.
It's going to be positive, right? So first thing we know is it's going to be positive. That's easy. Okay. Then if we know this value, let's just say this was changing at a rate of 1 molar per second. How fast would this, let's say this was changing at minus 1 molar per second, right? Minus 1 molar per second. How fast would this be changing? Twice as fast or half as fast?
Half as fast.
Half as fast, right? So if this was changing at 1 molar per second, this would be 0.5 molar per second, yeah?
Yes.
So given that this is minus 8.8 times 10 to the minus 3, what is this? And I see some of you already wrote it in the chat. It's going to be plus 4.40 times 10 to the minus 3 molar per second, right? Why do I know that? Because I know that the change in this has got to be twice the change in this from the reactant, from the balanced reaction. And I also know that since this is a reactant, this is negative. Since this is a product, this is positive. Are you with me? You see the difference between these kind of quantities, right, which are changes in the concentration of a reactant or product, and this quantity, which is the defined rate of reaction. It's two different things. Okay, here you go. Time to fly solo. So this one, I just want you to think about it just like we did this last one, okay? I'm gonna launch the poll. Oh, crud, I forgot to change the double D again. Okay, I gotta do that one of these days, but for now, just remember the second D is really E. I'm so sorry, it just like slips my mind every time. All right, so let me just talk you through this for a minute and see before you answer. You have this reaction. They're giving you the rate of change of O2, right? First of all, that's a product. Notice that it's positive. Okay? That's good. Now they're asking you for the rate of change. They're not asking you for the rate of reaction here at all. They're asking you for, given that the change in this is 0.0014, what's the change in H2O2? All right, so two things to keep in mind. One, it's going to be negative because it's a reactant, right? So you want to know that. And secondly, if you know that this is changing, and I'm going to use a different number here so you can apply to this one. Let's say this was going up by 1 molar. This would be going down by how much? There's a 2 in front of it. 2 molar, right? So just think about it like that. Go ahead and try to answer that question. Just think it through just like that. Okay, try to enter your answer in the next few seconds. I'm going to call it an end here. Okay, awesome, 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 awesome. Most of you put down the right answer, which is C, right? If this is changing, if this is 0.0014, right, positive, then this is minus twice that rate, right? Minus twice that change, sorry, okay? Now, so this question focuses on the rate of change of a reactant or product, okay? Now I'm gonna ask you a second question that asks you about the rate of reaction, okay? Remember, the rate of reaction has this definition right here. So apply this definition to this reaction and give me the rate of reaction. Okay, try to finish voting here in the next few seconds. Okay, very good. Very good. So the right answer was A. Again, most of you got that. A few of you got tripped up there. So let's just look real quick at what we're doing here. So they're giving us, right? They're giving us delta O2 delta T, right? And they're telling us that that's plus 0.0014 molar per second. That's the rate of change of a product, right? And that's why it's positive, yeah? So we're gonna go back to our definition of rate, right? And we see that for a product, the rate is 1 over the coefficient times the change in concentration of that product, right? What's the coefficient for O2?
1.
It's just 1, right? So the rate is equal to positive 1 over 1 times delta O2 delta T. Ah, perfect. So that's just 0.0014 molar per second. Got it? Okay. Great job. Great job. Thanks for paying attention. Thanks for participating in the poll. Let's move on now. So we have been able to define the rate of the reaction. Okay, so I really want you to pay attention here in the slight differences between the things we're defining. So we just defined the rate of reaction. Now we're going to move on to something different, which is the rate law. Okay, So the rate law tells us how the reaction rate, which we just defined, depends on the concentration of a reactant. Okay. If you have the reaction, so this is called the rate law, right? Keep that separate in your mind from this. What is this? Definition of rate. Okay. This is how we define the rate. Now we're going to see how that rate, which we just defined, depends on the concentration of a reactant. Okay. And the equation that gives us that is called the rate law. So if you have a reactant, A goes to products, right? We're going to define the rate law as rate is equal to K A to the N. Okay. And this rate is what we just defined. Okay. So we're saying that that rate is going to be proportional to the concentration of A. So in other words, if you have more A, the reaction might go faster depending on what N is. Okay. And this is the constant. So this is reaction rate. This K is called the rate constant. This is concentration of A, right? And this N is called the reaction order. Okay, that's called the reaction order. All right, and the most common reaction orders are N equals 0, 1, 2. N equals 0, we say that that's a 0 order reaction. If N equals 1, we say that's a first order reaction. If N is equal to 2, we say that's a second order reaction. And this N, what is the significance of that N? It specifies the concentration dependence of the reaction rate. Why is that? First of all, why is that important? Again, as a chemist, we want to try to control reaction rates. We want to know, okay, how can we make them faster? How can we make them slower, right? So we learned early on with the lizard analogy that one thing that reaction rates depend on is temperature, right? If you increase the temperature, generally what happens to the reaction rate? Did we learn from the lizard story?
Increases.
Increases, right? Now we're looking at, and we're going to come back to the temperature dependence a little bit later and explore that in more detail. But here what we're looking at is the concentration dependence. If I change the concentration of a reactant, what happens to the speed of the reaction? Okay. Well, it turns out the answer to that is not the same for every reaction. It depends on the reaction order. All right. If it's 0 order, then look what happens. Rate is equal to K A to the 0. What is A to the 0?
1.
What is any number raised to the 0?
0. 1.
It's not 0, it's 1. Okay. Any number raised to the 0 is 1. So this is really just equal to K. So for a 0 order reaction, how does the rate depend on the concentration? If I increase the concentration of a 0 order reaction, what happens to the rate?
It's unchanged.
Nothing, right? It's unchanged. Yeah? If N is equal to 1, then we have rate is equal to K A to the 1. If the reaction is first order and I increase the concentration of A, what happens to the rate?
It also increases.
It increases, right? It increases. For second order reactions, rate is equal to K A squared. For a second order reaction, if I increase the concentration, what happens to the rate?
Becomes exponential.
Right, it increases even faster. Okay, it increases even faster. So we could do a plot like this. If we were to monitor reaction concentration versus time for the 3 different orders, okay, here's what the concentration versus time would look like for a 0 order reaction. Now, let's remember that these are reactants, right? A in all cases. So notice that these lines are going down, right? Also, know that the rate or the change in the concentration with respect to time is equal to the slope of that line, right? So what do you notice about the slope of this line for a zero order reaction?
It's linear.
It's linear, right? The slope doesn't change. So that tells you that the rate doesn't change, right? Notice as the concentration of A drops, the rate's the same, right? Because for a zero order reaction, the concentration doesn't affect the rate. Yeah? Now let's see what happens to a first order reaction. Oh, the slope changes. It gets slower as the concentration goes down. Look what happens to the slope. It gets less and less steep, right? The reaction slows down. Why? Because as the concentration of A drops, the rate goes down, right? Rate is equal to Ka. You with me? And then for a second order reaction, the dependence is even greater, right? As the concentration of A goes down, the rate goes even less and less quickly, right? The rate is slower and slower, okay? Now here I'm gonna really throw you in for a doozy. Those of you that had calculus, you'll be able to understand this a little bit better. If you haven't had calculus, it'll be a little harder. But what I've plotted here basically is the slope of this line and the derivative of this line on this plot, right? And remember, the derivative is the slope, right? Is the rate, right? So basically what we're looking at here is the concentration versus time. And here we're looking at the change in the concentration versus the change in versus A, right? We're looking at the rate versus time. So we're looking at, not the rate versus time, the rate versus concentration, right? So I'm looking at the slope of this line as a function of A, right down here. So here's the point. And don't worry, don't get too tripped up by this, but I just want you to see this. This is the rate versus concentration. What do you notice for a zero order reaction? As you increase the concentration, what happens to the rate?
Constant.
Constant, right? Why? That slope is constant. Okay? Looking for a first order reaction. If I double the concentration, what happens to the rate?
It increases.
It increases, right?
They're the same.
And it increases linearly, right, with the concentration, right? In other words, from 0.2 to 0.4, notice this is a linear, right? Because even though this line, the concentration of A versus time is not linear, the slope is linear with A. What does that mean? If I double A, I double the rate. Now, look at the second order reaction. Again, this is rate versus concentration. If I double the concentration here, the rate is even more sensitive, right? The rate goes up exponentially with A. Okay? This is a little hard. There's a lot of information in this plot. So if you're not getting this 100% right now, don't worry about it. If you stare at it for a while and think about it, it'll start to sink in. But let's do some examples, and I think that'll help as well. Who had their hand raised? Sorry, was that you, Taylor?
Yeah. Is a good way to think of it for the second order like a parabola?
Yes.
Parabola.
Exactly right. Yes.
Okay.
Yep. Rate, because it's rate is equal to Ka squared, which is a parabola. You're exactly right.
Okay. All right.
Yeah. Totally right. Okay. Very good. All right. So one of the first questions we want to ask a reaction. So now that we learn how to define the rate, now we want to ask a reaction. Hey, what order are you? Are you zero order? Are you first order? Are you second order? I want to understand you, right? So what order are you, right? Because that's key to understanding how the rate depends on concentration, right? So if you want to control the rate, the first thing you're going to ask a reaction is, hey, what order are you? So how can you determine that? One way to do it is what's called the method of initial rates, okay? And in this method, what you do is you run the reaction several times at different initial concentrations. So for example, you'll run, let's say we just have this simple reaction again, A goes to products, right? And we're gonna say, okay, let's start with a concentration of A of 0.1 molar, and let's measure the rate for the first minute, all right? So we do that. And we get that the rate is equal to 0.015 molar per second. Then we run the reaction again, but now we double the concentration, right? So we start with 0.2 molar. We run it again for a minute and we see what the rate is. And we see, oh, okay, in this case, the rate went up to 0.030. We doubled the concentration. What happened to the rate?
It doubled.
It doubled.
It doubled. Oh, wait a minute. For which of these three does a doubling of the concentration result in a doubling of the rate?
First
0,
order.
1, or 2?
First order.
First order, right? First order, for a first order reaction. So we know, oh, great, for this particular reaction, if we had this kind of data, that would tell us right away that it's first order. Look, and we do it again here, 0.2 to 0.4. This goes from 0.03 to 0.6. So we doubled this and it doubled again, right? That's exactly what we would expect for a first order reaction, right? So if we were asking this chemical reaction, what order are you? And we had this kind of data, we'd say, ah, nice to meet you. You're a first order reaction. Are you with me? Okay, let's look at this data. So this is a different reaction, even though I'm just using generic A here, but this is a different reaction altogether. And I'm asking this reaction, hey, what order are you? And again, it's just A goes to products, really simple. I do the same experiment. I go from 0.1 to 0.2 and I look at the initial rate and what happens?
It's flat.
It's unchanged.
Unchanged. Well, for which of these three reaction orders would the rate be independent of the concentration?
0.
0 order.
Zero order, right? So when we meet this reaction and we do these experiments, we could say, ah, nice to meet you, you're 0 order. Are you with me? Now, let's look at this one. Here we go. Same thing. We're going to double the concentration and look what happens to the rate. It goes up by how much?
Quadrupled.
Quadruples, right? Which one of these, if I doubled the rate, would go up by a factor of 2 squared?
Second order.
Second order, right? Because it's squared. What would happen to a second order reaction if I tripled the concentration? It'd go up by how much?
9.
3 squared. So it'd go up by 9. Right? What if I quadrupled it? It'd go up by
16.
16, right? 4
16.
squared. Okay? So 0 order, change the concentration, rate is unaffected. First order, you double the concentration, you double the rate. You quadruple the concentration, you quadruple the rate. Second order, double the concentration, quadruple the rate. Quadruple the concentration, the rate goes up by 16, right? 4 squared. Okay, because it goes up by whatever you increased it squared. All right, very good. So let's apply this to a real reaction here. So this reaction has 2 reactants, NO2 and CO. And now if you have more than one reactant, you can have some order with respect to each reactant, right? So for more than one reactant, we'd write rate is equal to K A to the M times B to the N for a reaction A plus B goes to products, right? So we have the order with respect to A and the order with respect to B, all right? And so these are just coefficients, just like before. Sorry, these are the orders with respect to those. So we would say that M is the order with respect to A. And N is the order with respect to B. I'm just going to write with respect to B. All right. And for a reaction like that, we can also figure out the order, but we might have to do some more experiments, right? So let's look at this data right here. Notice that from experiment 1 to experiment 2, NO2 concentration doubled, right? CO concentration didn't change. What did the rate do?
Quadrupled, more or less.
Quadrupled, right? There's going to be a little bit of experimental error in these measurements, right? Because these are experiments that you do in the lab, and so they're not always going to be exactly perfect, right? But notice, I doubled this, I didn't change this, and this quadrupled. So what can you tell me? What is the rate with respect to NO2? I'm
Second
sorry,
order.
what is the reaction? What is the order with respect to NO2?
Second order.
Second order.
Second order, right? Second order. Okay, let's go to these two experiments. Well, actually, let's go to the 2 and 3 here, right? So here, I don't change NO2, but I double CO. And what happens to the rate?
It's the same.
It's the same. So what does that tell you about the order with regard to CO?
0.
0th order.
0 order. Okay, 0 order. Does that make sense? All right, let's try
I'm
one
sorry,
more.
one more
Question.
like, so that would be the total reaction would be order 2? Or it's
Oh,
3
good.
'cause you
Okay,
add-
yes. So overall order of a reaction with more than one reactant would be M plus N, would be the sum of both of those. So yes, what we'd say about this reaction, here's the rate law, right? We'd say it's second order with respect to NO2, 0 order with respect to CO, and second order overall. Overall means just the sum of the two reaction orders. Okay? All right, let's try another one. Let's determine the rate law. And this time I want to also get the rate constant. So I want to get both of these things. I want to get the rate law and I want to find what K is. Okay? So here, let's look at what happens. I triple the concentration of ammonium, NH4, a reactant, right? I triple it. I hold this constant, and what happens to my rate?
Triples.
Triples, right? So rate is equal to K times NH4. What's the order with regard to NH4 plus?
First.
First order, right? Then I'm going to go down here and I look at these two experiments because those two experiments hold this variable constant and it doubles NO2 minus. And when I double NO2 minus, what happens to the rate?
It doubles.
It doubles. So what do I know about the order with regard to NO2 minus?
It's order 1.
Order
Or
1
first
as
order.
well. It's also first order. Okay. So then the next thing I want to do is find the rate constant. I want to find this thing. Well, how am I going to do that? I can use any of these entries, plug them in, and then solve for K, right? So I can say K, because K is going to be equal, if for a given concentration I know the rate, K is going to be equal to the rate at those concentrations divided by those concentrations, right? Raised to the appropriate orders, right? But in that case, it's just 1 for each one, right? So I'm just going to plug into that. And I'll use experiment number 1, this one, but I could use any of them, okay? 10.8 times 10 to the minus 7 molar per second divided by the concentration of NH4 plus at that rate, right, which is 0.02, divided by the concentration of NO2 minus, which is 0.200. Are you with me? And if I just plug that in my calculator, I get 2.70 times 10 to the minus 4. And the units here are a little funny. And I forgot to put in my units here. So this is, remember, this is molar, right? So one of these is going to cancel out, and I'm going to end up with molar second in the denominator, right? Because one of these molars cancel. I have seconds in the denominator, I have this molar in the denominator. So it's molar second in the denominator. Let's see, I see a question from Seth Williams.
I just had a question regarding like the N values. So like on the
Yes.
first one where we said it tripled,
Yes,
so we just said it was for first order. If it's
correct.
like within, so if it's underneath 4, so if it doesn't quadruple, we're just
No,
gonna say
no,
the first
okay, now
order.
be careful here. In this example, we doubled the concentration. Sorry. Let's look at for this guy, we doubled the concentration and we saw a doubling of the rate. Okay. For this guy, we didn't double the concentration. What did we do? Tripled it.
Yeah.
Right? So because we tripled it, and then this went up by a factor of 3, that tells us that it's first order. If we triple the concentration and it were to be second order, what would it have gone up by?
Gotcha.
3 squared, which is 9, right? So we're not rounding here. This is exactly what we expect for a first order reaction. Triple the concentration, triple the rate. Quadruple the concentration, quadruple the rate. Right? It
Gotcha.
just depends on what happens over here. And so in this case, the concentration change was different. We didn't just double it, we tripled it. And that tripled the rate.
Sweet. Thank you.
Yep. Good. Good question. Diana.
I just want to make sure that I'm understanding it right. If
Yeah.
the concentration goes up by the same amount as the rate, then it would be 1, right?
Correct.
If it the concentration goes up by 2, then the rate would have to quadruple. That would be 2.
Yeah, that would be 2 second order. Correct.
And if they all stay the same, that would be 0.
Correct.
Okay.
Yep. Yep. Good. Good, good, good. All right. You ready to try one? Here we go. Remember that in this poll, there's 2 Ds. Okay, so disregard this second D because there's only 4 answers. So no one should be answering the second D. So sorry, I will get this fixed.
At least we know which D to click on, so
Yeah.
that's good.
Yeah, I'm so sorry, you guys.
Figuring out which D to click on is like the easiest part of this class.
Awesome. Thanks, Rylan. Love that. Oh, that was funny. Okay, try to put your answer in the next 10 seconds or so. Okay, last call, and I'm going to end it. Wow, you guys are really on it for a Monday. That's awesome. The correct answer was B. Most of you got that. It's first order. Okay. Let's just look at why. So we're looking for the order with respect to OH minus, right? Now, one thing some of you might have done is you might have looked at this 2 and selected 2. This coefficient has nothing to do with the order of reaction. Okay? So if you did that, that is a common misperception that a lot of people have, that this coefficient tells you the order of reaction with regard to that reactant. That is not true. Okay? This coefficient is not related to the order of the reaction. How do you get the order of the reaction? You can't do it from the coefficients in the chemical reaction. We define rate, right, with regard to those coefficients, right, earlier. That's why I'm saying you got to keep the idea of rate, the definition of rate, different from order, right? Those are two different things. This is the order of the reaction. This tells you how the rate changes with concentration. So you have to look and do an experiment to determine that. So notice what happens here. For OH minus, you can look here where it's easiest if one thing is held constant and only one thing changes, right? So here, this is held constant and this is changing. This goes up by a factor of 3. What happens to the rate?
Goes up by the same
Ripples.
factor.
Goes up by the same factor, right? So what does that tell you about the order with regard to OH minus?
1.
First order.
First order. Okay, very good. All right, one more question for you. Now it's asking for the order with respect to ClO2. Be careful when you read this graph with these numbers, right? This is 0.0248. This is 0.00276. Okay, there's an extra 0 here compared to there. Okay, try to answer in the next few seconds. All right, very, very good. And the right answer was C, second order. And again, most of you got that, so good job. You're paying attention and you're doing great. So why is it C? Let's look. So we're looking now at the order with respect to ClO2, all right? So here, from here to here, the concentration of ClO2, in this case, goes down by a factor of 3. But of course, we could read it the other way. We could read it from here to here. It goes up by a factor of 3, whatever you prefer, okay? But let's just think about it going down just so we understand what happens, right? If a first order reaction were to go down by a factor of 3, the rate would go down by a factor of 3. If a second order reaction concentration were to go down by a factor of 3, the rate would go down by a factor of 9.
9.
Right? 9, exactly right. Okay. So since this went down by a factor of 3, we would, and then this went down by a factor of almost 10. You can almost see that it's almost 10. It's not quite 10. It went down by a factor of 9. Then you know that it's second order with respect to ClO2. All right. So this reaction is first order with respect to OH minus, second order with respect to ClO2. Again, notice there is no correlation between order of reaction and these coefficients, right? No correlation. You can't use these coefficients to determine order of reaction. I know, sorry about that. This was tricky to see, that extra 0. So some of you missed it because of that, but that's great. That means even more of you got it right. Okay. All right. Any questions about reaction orders? All right. How many, let's see, how can I, oh, I'm going to launch a poll. I'm just curious. How many of you have had calculus? A, yes. B, no. Okay. All right. A good number of you have had calculus. Looks like about 80%, almost 80% of you. So 80% of you have. So I'm going to do a little calculus just kind of for fun. You won't have to know this, but it's just kind of for those of you that have had calculus, you can kind of just see how it can be applied here. And for those of you that haven't, just listen up and at least you'll understand why. Yeah, for fun. Hard to believe, right? So again, remember in this chapter, it's very important to keep all these different ideas sort of in their own categories, all right? And not mix them up because the tendency is to mix things up here. So definition of reaction rate, right? That's one category of thing, right? Where we define reaction rate. The effect of concentration on the reaction rate. That's a separate thing, right? The rate law, 0 order, first order, second order. We just covered that, okay? Now, the rate law tells us the dependence of the rate on the concentration, right? That's the rate law. What we're going to look at now is something called the integrated rate law. And it's called integrated because in order to get it, you have to integrate calculus, the rate law, right? Integrated rate law. This quantity here, this equation tells us rate versus concentration. The integrated rate law is going to tell us how the concentration changes with time. All right. So in other words, the rate law tells us, hey, Mr. Reaction, are you a 0 order reaction, a first order reaction, or a second order reaction, right? What are you? What's your order? This is kind of, it's going to tell us, okay, Mr. Reaction, if I start out with 1 molar of your reactant, right? How much reactant am I going to have after 30 minutes? So in other words, this tells us how the rate changes with concentration. This tells us how the concentration changes with time. All right. If I start out with a particular concentration, how much am I going to have after a given amount of time? All right. In order to do that, I have to integrate the rate law. So let's do a little bit of calculus just for fun, just for funsies. And we'll start with a first order integrated rate law, first order. So we have the reaction A goes to products, right? If that's a first order reaction, we know that the rate is equal to k times a, right? So far, so good. Now, let's go back to our definition of rate. For this reaction, how would we express the rate with respect to that reactant? Go back to our definition of rate. How would I expect the rate? How would I express the rate for this reactant? First of all, plus or minus?
Maybe minus.
It's a product. I'm sorry, it's a reactant, right? So it'd be minus. And what's the coefficient out here?
1.
1. So it's 1 over 1, which is just 1,
Mhm.
times delta A, delta T. But we know these deltas are, we know that in calculus, right, the deltas are really dA dt, right, the derivative. So if we write this, not using the deltas, but we write the instantaneous change, right, which is what you do in calculus, we would write rate is equal to minus dA dt, right? So there's our calculus. The rate is equal to minus the change, the derivative of the concentration of A with respect to time, all right? So what I'm going to do is I'm going to use this definition and I'm going to plug it in right here. All right. So I'm going to take my definition of rate and put it into the rate law. All right. So what do I get? Minus dA dt is equal to Ka. All right. That's just my rate law with the definition of rate plugged in. Okay, that's all that is. Now, what I want to show you is how we get to the integrated rate law. All right, so let me go to another page and I will just copy this. Minus dA dt is equal to Ka. Okay, so the first thing I'm going to do is I'm just going to move the negative sign to the other side. So I get dA dt is equal to minus Ka. Now, for those of you that have had calculus, you might recognize this. This is a special kind of equation. It's called a differential equation. So a differential equation is an equation that expresses the rate of change of something. The rate of change of something, right? So you, like in calculus, you might have done things like dx dt is equal to kx, for example, right? But now x is just can be anything, right? But in this case, it's concentration, right? So does anybody remember from their calculus class how you solve this equation? Remember, when you solve a differential equation, you have the derivative of A with respect to t, but what we really want is A with respect to t. Okay? Anybody remember how to do that?
You multiply by dt and then take the integral.
That's right. Very good. You multiply both sides by dt and then take the integral. So I'm going to multiply this side by dt. Again, if you haven't had calculus, don't worry about this. This is not, you're not responsible for this. This is just purely for entertainment. So dA is equal to minus Ka dt. Right? So that multiplying both sides by dt. And then what do?
Take the
Integrate.
integral.
Then you integrate, right? Then you take the integral. Oops, I forgot one thing. What do we forget? You gotta separate the variables. So I gotta keep the variables together on each side, right? So before I integrate, I gotta do one more thing. Does anybody know?
Separation of variables.
Yeah. So I gotta divide by A. Right. So I get dA over A is equal to minus K dt. Now I can integrate. This is just a constant, so you can pull it out of the integral, right? I'm going to integrate this from A0 to A. I'm going to integrate this from time 0 to time t. Okay. And now let's see how many of you remember your integrals. What's the integral of 1 over x dx?
Natural log.
X.
The natural log of x. Okay, the
Plus
natural log of x. Very good. So what I get here is the natural log of a, and I'm evaluating that from a0 to at. All right. And then on this side, what's the integral of dx, of k dx? What's this
X.
integral? Just x, right? Kx, sorry. Kx. So minus k would have a minus. So that's equal to minus kt from 0 to t. All right. So then I get that the log of a of t minus the log of a0 is minus kt minus k times 0, which is 0. Elliot, Cook, where are you? You have a question?
My bad. That was from earlier.
Oh, no worries. Okay. So we get that equation. So that's one. This equation here, and there's another form of it. I can also write that as log of a of t over a0 is equal to minus kt, right? And this is called the integrated rate law. And this is for first order, because they're going to be different for the different orders. Okay. Notice what this gives me. There's no plus c because this is a definite integral, right? It's from a0 to t, so there's no plus c. So again, if you haven't had calculus, you can not worry about any of this, but this you have to worry about. These are the equations that I wanted to show you and the equations that we're going to be using. This tells us how, if we know an initial concentration of a reactant and we know the rate constant, then we can find the concentration at any time later, right? That's what these reactions, that's what these give us. Remember, they're giving us concentration versus time. Concentration versus time. Are you with me? Ryland.
For the bounds on the dA integral, you integrated from a0 to a plus. I'm a little confused by what's going on.
Sorry. Yes, I should have been clear about that. From a0, which would be the initial concentration. Okay, yeah. Let me. Thank you for asking that question. Let's define all this stuff. So A of t is concentration at time t. Oops. Okay. A0 is initial concentration. All right. K is our old friend, the rate constant, which we already have met. Right. And of course, T is just time. Right. So what this equation is good for is it's exactly what we talked about just a couple minutes ago, right? If I know the initial concentration, how much is left after a certain amount of time, right? So for example, let's say you had, years ago, we used to use chlorofluorocarbons in a lot of solvents and in a lot of aerosols. So these chlorofluorocarbons had chlorine in them, and they would contribute to ozone depletion. Have you guys heard of that? Have any of you heard of that? Okay. So they've been banned. So one thing, for example, you could use an equation like this for is to say, okay, if I have a certain amount of chlorofluorocarbon in the atmosphere now, and I know the reactions that break it down, how much will I have in 20 years? Right? That's an example, right? Or if I have, if you have a rocket and it's burning fuel, and I know the amount of concentration that you have now, how much will I have 20 seconds after liftoff? Right? It's those kinds of problems that this integrated rate law addresses, right? I have a certain amount now, how much will I have in 20 minutes? Yeah? The other thing I want you to notice about this is that this also gives us another way to determine the order of a reaction, right? I just showed you a minute ago how to determine the order of a reaction by the method of initial rates, right? But here's another way I can do it. I can just measure A. So I can make a bunch of measurements where I measure A, at different times, right? So I have, let's say A, the initial A at time 0 was 1 molar, right? And then in, 20 seconds, it goes down to 0.8 molar and so on, right? So I have a bunch of data here where I measure the rate, I measure the concentration at different times. Look at what this equation looks like if I write Y, I should rearrange this to make it a little bit more clear. Let me bring this down here and rearrange it just a little bit. Log of A of t is equal to minus kt plus log of A0. Okay. All I did was I brought that minus log A to the other side. And I have an equation that looks like Y is equal to mx plus b. In other words, if I make a plot of log of A versus time, right? This is telling me that this is going to produce a straight line, right? Y is equal to mx plus b. Here's the slope. Here's the slope. So that slope is equal to minus k. And what would be the intercept?
The natural b, your natural log.
The natural, it'd be this, right? The natural
yeah.
log of A0. So the intercept would be log of A0. Cool, right? So you can just figure out the order of a reaction just simply by monitoring the concentration as a function of time. If it's first order, you would make a plot of log of A versus time. And if that's a straight line, bam, first order. Okay? And from the slope, you can get the rate constant K. Let's see. I know most of you are probably pretty familiar with logs, but we're going to be dealing with logs in this chapter a little bit and in the chapters that follow. So if you're a little rusty on your logs, it might be a good time to review that. One of the appendices in your ebook has a nice little review of logs. So you might want to go to that. But just remember, the log of a number is what number? The log of a number is the number that is the exponent this has to be raised in, the 10 has to be raised in to get that number, right? So the log of 10 is 1. Why? Because you have to raise 10 to the 1 power to get 10, right? And log is a base 10 log, all right? So here, the log of 100 is, okay, so if you didn't know it was 2, you'd say, what number do I have to raise 10 to? It's always, if it's log, it's always what number do you raise 10 to get this number, right? So what number do I raise 10 to get 100?
To the power of 2.
Power of 2, right? Again, log of 1,000, what number do I raise 10 to get 1,000? 3. What number do I raise 10 to get 10,000?
4.
4, right? Everybody see that? So the log of a number, log of a number, is simply what number do I raise 10 to get that number, to get the number that I'm taking the log of, yeah? Notice that for numbers greater than 1, the logs are going to be positive. The log of 1 is by definition what? Does anybody know?
0.
0. The log of 1 is by definition 0. So if you have a number greater than 1 and you take the log, it's going to be positive. If you take the log of 1, that's 0. And if you have a number less than 1, then the logs are going to be negative, right? In other words, what number do I have to raise 10 to get 0.1? I have to raise to minus 1, right? What number do I have to raise 10 to get 0.01? Minus 2, okay? The log and the inverse log are functions that undo each other, right? So the log of 100 is 2. The inverse log of 2 is 100, all right? And the inverse log undoes the log, basically, right? So the inverse log of log 100 is just 100, right? Because they undo each other. inverse log of x is just 10 to the x. Okay. So if you take the inverse log of a number, you just raise 10 to that number. All right. So the inverse log of 3 is 1,000. The natural log, instead of using the base 10, it uses the base, which is 2.71828. Okay. And that's what I'm using here is the natural log. All right. And, but the natural log and the regular log have very similar properties. The only difference is instead of 10 being raised to the power, it's this number being raised to the power. Okay, a couple other important things about logs. The log of a product is the sum of the logs, right? Which is what I did. The log of a product is the sum of the logs. The log of a fraction is the log of the numerator minus the log of the denominator, right? So in going from this equation to that equation, I use this relationship. Log of a to the n is equal to n log of a. All right, and that's true for both base 10 and natural. I know that was really quick. Just a quick reminder of logs. Again, if you don't remember this stuff, just go to the appendix in the book on logs, and I think it's appendix, I can't remember off the top of my head, but it's one of the appendices in the book. You'll find it, and it reviews out math, and there's a section in there on logs. Okay. All right. We're all out of time. You guys have been really great today. Thank you for your participation. Thanks you for your attention. And I hope you have a great Monday, great Tuesday, and we'll see you on Wednesday. Again, I'm going to stick around to answer any questions you might have for my office hours. So I'll be here. I'm going to take a quick break just for a couple minutes, and I'll be back. So stay tuned. If you have questions, just stay on the line, and we'll chat. Okay. Thanks, all of you.
Thank you.